mic check. Good morning. Oh, music's too loud. All right, let's get started. Good morning. How's everyone doing today? If you're in the chat live, say hi. How's it going? So I did get a comment. I saw that the chat wasn't working for somebody live. So I just wanted to clarify and ask questions, and definitely email me because I'm so the whole point of my live streaming is the chat, and that's why I went to YouTube. So I'm a little disappointed if people can't figure out the chat on YouTube. So for context, I used to use Twitch. So that's where I usually used to do these live streaming lectures, but no one ever knew what Twitch was. So I'm trying YouTube this quarter, but if YouTube isn't working, then I might want to consider moving to Twitch or something where we can use a chat function, because that's how this whole thing works. Is you chat me and I get feedback, kind of like a really fast-paced chat environment. So yeah, email me, give me feedback. We can switch to Twitch if that works. I was hoping YouTube would be more universal, but if it's not the case, let me know. So a couple of reminders and kind of course info. So don't forget, Lab 1 is today. If you are in our live session, we'll be meeting for lab at 2:30 if you're doing in person. And if you're doing it online, so the video is already posted. It's there for you to watch. You just have to go through kind of the reaction, watch it, and see what you observe. All right. Oh, and then one other thing I forgot so I updated the syllabus. So check out the syllabus. So for some, I don't like the new concourse system. I don't want to complain too much, but I feel like there's always something weird about my syllabuses now and some error. So I updated it. It was somehow missing the exam 1 date. So exam 1 is coming up. That's going to be week 4. So that's our first exam. So I just want to put that on your radar. And how the exam's going to work is I'm just going to open it up. I should probably open it up early for people that want to work ahead. I'm just trying to go the pace of the course, but I'll open it up. It'll be available through Blackboard. And again, kind of at your own pace. And then so one other thing, so labs, I added everyone to Gradescope. And so the lab will be turned in to Gradescope. And so people should have gotten an email saying that you were added to the class. Other questions, comments? So let's start with the next half of this chapter. So functional groups. So I just kind of put our cheat sheet up here of all our functional groups. So functional groups are just groups of atoms that have characteristic chemical reactions and properties. And so today we'll just kind of go through all these groups and mention, some of their properties, how to name them. And this is a good crash course of kind of OChem. And so let's start off. It'll be a slight recap. So we're starting with alkanes. So alkanes are just those simple hydrocarbons. So no double bonds. So only single bonds. And so they're just named by, how many carbons they have. So methane, ethane, propane. Let me see if I can find, because I realize that your books doesn't have a prefix. There we go. This is what we need. Let me copy this. I'm sure your book has it somewhere. It's just hiding. So for naming, we have all these prefixes, and this will help us for all of it. Okay, that wasn't quite what I wanted. But here we go. So here's all our prefixes. So propane, butane, pentane. So all these tell you the number of carbons. And again, the alkanes will all end in that ane. So butane. So that's 4 carbons. And practice your skeletal structures. So 1, 2, 3, 4. Butane. Pentane. 1, 2, 3, 4, 5. And this would really be N-butane and pentane to show that they're in a line. So you just continue so you can look at these prefixes. So hexane. Hexane, I'll note, I just want to draw your attention to it because this is actually a toxic compound, at least more toxic than people realize. So hexane is a really commonly used solvent. It's used to clean up oil spills. So let's start talking about, some of those things. So looking at this molecule, it just has CHs. And so do you remember kind of our property of polarity? So determining polarity. So this is a bit of a recap. At least it should be from 104. But previously, so we try to determine whether things are polar by, first we had to determine whether the bond was polar. And so we did that by determining the difference in electronegativity. And we said greater than 0.4 means that it's a polar covalent bond with that uneven sharing of electrons. But then we also had to determine whether the overall then dipole moment canceled out or not. And so what we mean by that is if we take dichloromethane, so 2 chloros, and the rest is still like methane, versus, let's just do carbon tetrachloride. So in this case, we know that our carbon-chlorine bonds are polar. And so I would go ahead, and this is to kind of help you to draw your arrow showing where your electron negativity is going towards, so where your electrons are going to be drawn towards. And so if we do the same for our carbon tetrachloride, so what do you notice about that? And so do you think which one's polar, which one's non-polar? So I'm going to build a little molecule kit really quickly. And this is where the 3D geometry really helps. A little messy there. So here's our molecule. So this is our carbon tetrachloride. And so if we're imagining, right, we have our arrows pointing out in each direction. The thing is, it's symmetrical, right? So it's completely symmetrical since it's tetrahedral. And so even though, yes, each individual bond is polar, because overall they're all going out kind of evenly, right? So it's all even. There's no one side that kind of has more electron density, right? So it's all being pushed to the outer edges here of our chlorine, but then that's all symmetrical by rotation. So let's compare that to the dichloromethane example. And so all I'm going to do is swap two of those chlorines, and notice how halogens are usually represented by green balls. So I just replace them with my white balls now. But we can see if we orient it, let's just orient it like that. And so you can tell that this side is going to have more electron density, right? So the electrons are being pushed out this way. So we have electron density localized on this side of the atom, right, where the chlorines are, or the molecule, excuse me. And of course, over here is our hydrogens. So they're going to be left with less electron density. So remember, hydrogen only has one electron anyways. So it's fairly easy to strip that electron from it. So this is going to be where, kind of partial positive side, partial negative. And so going back to our sheet here, so this means that dichloromethane would be polar, and this is nonpolar. And so now you may be asking, okay, what was the point of that? But let's go back. So let's look at hexane. And so this is relevant because we kind of want to guess, well, what dissolves in what? How do we know what solvent to use in what situation? And so we find hexanes, and why it gets used so often is so hexane, so it's just CHs. So this is going to be nonpolar. And since it's nonpolar, this means that it's good at dissolving like oils. And so anytime you have some sort of oil spill, usually, people try to use hexanes to clean it up since it is effective. And so this we'll start touching into this concept of like dissolves like. You may have heard that before. But basically it has to do with how the molecules interact. So if they're similar in properties, that means that they're going to interact then and dissolve. So again, that's why hexane and oils would dissolve. So then continuing on, so now we have alkenes. This is going to get, actually I'll start a new section just so I can write my notes of all of our functional groups there. So alkenes now have a double bond. And so of course you can still use all these same prefixes that we have here. So ethene, that'd be our carbon. So one carbon. And then so the next question is, so how do we name other compounds? So ethene, how do we indicate where our double bond is? So let's look at the next one. So we have propene. So propene, 3 carbons, 1, 2, 3. So this one doesn't matter, right? And what I mean by that is, so we could draw the double bond there, but then we could also put the double bond between these 2 carbons. However, what do you notice? They're symmetric, right? By rotation. So they're the exact same molecule there. So now let's look at butene. So how do we name this? How do we indicate what the double bond is? Let's look at a couple of examples. So let's look at 1-butene. So 1-butene, so we need 4 carbons, 1, 2, 3, 4. And then if we have a 1 here, this is indicating where our double bond is now. So it's saying we have our 1 double bond, and it starts at carbon 1 there. So there's our 1-butene. So what would 2-butene look like? Take it a minute or so, 30 seconds. So what does 2-butene look like? So now we can draw this again. 1, 2, 3, 4 for my 4 carbons. Now the 2 is telling me that the double bond starts on that second carbon. So now this is 2-butene. And so what about 3-butene? Is there a 3-butene? And so the answer is going to be no. So if we were to draw this, so starting on the 3rd carbon up, what does that look like? So you always start the carbon labeling with kind of the priority group. And I'm trying not to make this too complicated because organic chemistry naming is pretty complicated. But so we have here that our carbons are always numbered in priority. Priority means, like, does it have substituents? Does it have double bonds? So all those give it different priorities. But in this case, since now we have the double bond on this end, this makes this carbon 1 again. So really there is no 3-butene, right? This is just equal to 1-butene again. So does that kind of make sense? And of course we could continue on. So butane, and then pentene. And so can you draw out all the isomers for pentene? What might that look like? So try 1-pentene, 2-pentene, 3-pentene. Give everyone Just a few seconds. All right. So 1 pentene, so I'll draw out my 5 carbons. 1, 2, 3, 4, 5. So 1 pentene, 2 pentene, is there a 3 pentene? What do we find? So if we were to draw that, 1, 2, 3, up, 1, 2, so this is equal to 2 pentene again. Looking at your book, and I realize you don't go into this much detail for all your functional groups. So alkynes, similar pattern. So let's look at some other groups now, so we don't spend too much time on everything. So let's look at alcohols, ethers, and epoxides. So alcohols, notice, are just some carbon chain ending in OH. And also, if you have questions, like, really feel free to interject. This is your time, as well. If you have some other burning questions in the chapter. So alcohols, so anything ending in that OH group. And so you can see that they're named ending in all. So ethanol, that's the one you drink. So ethanol is 2. So 2 carbons plus my OH there. So ethanol, let's look at, so you could also have hexanol. So now that's 6 carbons. So 1, 2, 3, 4, 5, 6. And my alcohol. And so similarly, you can use the numbers to indicate where your alcohol is. So these are usually just implied, like 1 hexanol, so starting on that first carbon. But let's just say, what if you had 3 hexanol? So write out your carbon. So 1, 2, 3, 4, 5, 6. Did I do that right? 1, 2, 3. Always count your carbons and then double count them. Like that will get you through OChem, is counting your carbons. So 6 carbons and then position 3. So 1, 2, 3. And now I'll put my OH there. So that's 3 hexanol. And so I wanted to look at these. So let's put up ether and epoxide there as well. So ethers are anything with the oxygen in the middle. So everyone likes this molecule. So this is diethyl ether, or in Halloween time, it's diethyl ether bat. So again, oxygen in the center, diethyl. So we have 2, right? Ethyl for 2. So 2 on each side. That's what that di means. So diethyl ether. Let's see, your book mentioned MTBE. Just trying to find where it said that. and what it said. So MTBE, many of you may have heard of this solvent. So it's a pretty common solvent, but I think it is banned in some places. Not terribly sure why. Yeah, there we go. I found it in your book. So it says MTBE is now of environmental concern and it is water soluble. So let's break down what this is. So the name for MTBE is methyl tert butyl ether. So what does that mean? So it's similar to this diethyl ether when you kind of analyze the naming structure. So if we go back, ether has to be oxygen in the middle. And then so we have a methyl and then tert butyl. And so butyl is 4, and I'll just tell you this tert butyl group. This is what it looks like, where you have 1 carbon in the center attached to 3 carbons. And so this is MTBE here, methyl tert butyl ether. And so what we're getting at, and let's throw in epoxides because I said we would talk about epoxides. They're just less so. So epoxides have this interesting circle here. So notice there's still an oxygen, but then it's bonded to 2 carbons there. What I wanted to focus on is what it dissolves in and kind of its polarity. So we're talking about polarity. And so if we have this OH here, do you remember what type of bond this is? Or I think we discussed it previously. It's a special case. Or what do you know about alcohol and water too? So you probably know that, the alcohol you drink is a mixture of ethanol and water. And so we have this OH group here. So remember OH group as hydrogen bonding. And we had said that this was a really special scenario of a very polar bond, right? So the oxygen is extremely electronegative. And so remember we have hydrogen bonding anytime hydrogen is bonded to nitrogen, fluorine, or oxygen. And so these elements are very electronegative. So we were saying that hydrogen can be easily stripped. And so the oxygen is pulling that electron density towards it. And so hydrogen kind of gets our partial positive charge. And so let's kind of recap from water. So that leaves us with oxygen having a partial negative charge, these hydrogens having a partial positive. And so you get this same effect here with those alcohols. And so that just means that these alcohols are going to be polar, so then they can dissolve polar things. That goes back into this like dissolves like. So this alcohol is going to be miscible or dissolved in water. So alcohols, say polar, water soluble. And so ethers and epoxides are similar, so they kind of start decreasing in polarity. So alcohols are going to be the most polar, most soluble, and then ethers also tend to be polar and soluble. But if you were to notice, so this ether is kind of in the center, so that kind of balances that electronegativity. Plus, it doesn't have that hydrogen bond on there, so having that OH really makes it polar. And so the ether, still polar from our oxygen, but not as. And so this is where the concerns from MTBE come in, though, since MTBE is water soluble. And so this causes some concerns. And so same with epoxide. So again, they're going to be a little less polar than ethers, but they're probably still water soluble. Looking for questions. All right, so that was those groups. So let's just look at kind of these other groups that we have here. So of course, haloalkanes. That's just anything with a halide on there. So we could do chloroethane. So now that's just 2 carbons, chloro on there, chlorine on there. So what about, so let's look at some other examples. So what if I gave you dichloroethane? How would you name that? How would you draw that? Are there different ways to draw that? Give everyone a minute or so. So what do we get? So this one, dichloroethane, we could draw it 2 ways. So we could draw a chlorine on each carbon. So this is 1,2-dichloroethane to indicate that you have a chlorine on each carbon. But there's another way to write it as well. So we could have put a chlorine, 2 chlorines on 1 carbon. So again, these would be isomers now. So same chemical formula, different connectivity. And so this would be 1,1 to show that both chlorines are on that first carbon, dichloroethane. Let's see. So what else should we look at? So let's look at these aldehydes and ketones next. So an aldehyde is different in that it's terminal. So notice aldehyde is this C double bond to O with an H at the end versus a ketone where that carbon's going to be in the middle there. aldehyde. RH versus ketone. And so what do we think about the polarity of these? So our CO, these tend to be polar as well. And so sometimes what can happen is you have a different group here, and then the electrons can get pushed onto that oxygen. And so that can make it prime for reactivity. So let's look at just some naming as well. So let's see, let's do one example. So looking, and there's all sorts of exceptions. So it says naming as all, so ethanol, but you may also see like ethanaldehyde. So let's look at, so ethanol. And this is why naming gets kind of funky, is there's exceptions and different colloquialisms. So this is ethanol, but I think that's just really hard to distinguish from ethanol with an O versus ethanol. And so usually, and this is the name that I'm more familiar with, is acetaldehyde. So that's just kind of the common name. So this is the simplest one. So this would be methanol. But I've never heard it called that. So formaldehyde is what this is. So this is a preservative to use to like preserve dead bodies. And this is also very toxic. So you don't want to get exposed to large amounts of it. And then let's do another one here. Now I'm drawing out the structure. So how would we name this? So let's look at it. So I have 1, 2, 3, 4. 1, 2, 3, 4, 5 carbons. I have a chlorine here, so it's on the second carbon. So this is carbon 1. And again, you just start labeling from either end. So you kind of pick like which end has the highest priority. It's going to be this end since it has a carbon on it. So 1, 2, 3, 4, 5 for our carbons. So then it's going to be 2 chloro and then pentanol. And let's see, let's look at some ketones. So ketones are just ending with -one, so propanone. So propanone. So of course ketone has to be in the center. So that's how we know it's in the center there. 2 carbons on each side. This is also known as acetone. So very common solvent. So again, this is also going to be fairly polar. So from that CO group there. Let's do another practice. Oops. Sorry, too many carbons. One, two, three, 4, 5, 6. So what would this be? Let me redraw this. That's supposed to be a single bond. It looks like I made a bad double. So we have 1, 2, 3, 4, 5, 6 carbons. Our ketone is on our third carbon. So we want to name it 3. Then for 6, we use hex, so hexanone. And apparently common name, so sometimes you might see it as ethyl for this group, propyl for this group, 1, 2, 3, ketone. So then looking at what's next, so we have the carboxylic acid. So carboxylic acid, this is also going to be really polar. It's also, going to be acidic. It's going to be an acid. And so you can identify that carboxylic acid since it's really distinct with this C connected to a double bond and an OH group. So carboxylic acid. And so these are really important. So they can get deprotonated. They can lose that acidic H there. And then why this is so stable, and we'll learn this, is you can make resonance forms. And this is also why it's kind of our acid. Let me redraw this here. I just want to draw it more explicitly. So this is our oxygen, our negative charge on it. But what we could do is take these 2 electrons, make a double bond. Now this puts the negative charge on that other oxygen. And so that resonance structure helps to stabilize it. And that's why, it's kind of favorable to lose that proton, since we can stabilize this negative charge across the 2 oxygens. So that's carboxylic acid, acid anhydride. So this is, again, a little interesting scenario. So we have oxygen flanked by 2 carbons, so 2 carbonyl groups here. So esters, we have now an oxygen attached to not a hydrogen. Again, these are all going to be polar. So amides, now it's connected to C double bond. So compare amides to amines. So let's just look at those 2. So amides versus amines. So again, amide, you have a carbon double bond connected to some sort of nitrogen group, versus an amine is just any nitrogen. And then not to be confused with imine. So imine is a special C double bond nitrogen group. Let's see, we also have nitriles. So let's look at, let's name some amines just for kicks. So what's the name of this one? Let's draw it. I'll redraw it. This is kind of a joke too. So this just has one. So this is going to be methylamine. And why I brought this up is so methylamine, this is made kind of famous by Breaking Bad. So I don't know if you watch Breaking Bad, but this is the compound that they were stealing from that train. And of course it can be used in drug synthesis, but I just want to point out that it's an amine. It's very simple. And so, you know, it's a very desirable group anyways in organic synthesis. And it, you know, has nothing to do with just making meth. But unfortunately, you know, with the popularity of Breaking Bad, that gave methylamine kind of a bad rap and put it under more scrutiny. So now it is a regulated substance. Very hard to get. So then, where were we? So let's look at nitriles. I just wanted to bring up one of these nitrile groups. So nitriles, we have a carbon triple bonded to an N. And so the common one I'll bring up, and you may have heard of this. So it's commonly known as acetonitrile. And I will draw it, and then I'll see if you can guess the IUPAC name for it. And if we go back to how it's named here, so we say whatever prefix and then nitrile. So looking at this one, it has 2 carbons, so that brings us to ethane nitrile, or how to name that. Let's see. So then we have isocyanates. This is a fairly distinctive group. So N, double bonded to C, double bonded to O. Azo compounds. So these are azides. These are explosive. So my lecture notes, there are 2 different lecture notes. So my lecture notes should be prominent. Let me look. So today's, I didn't update them from the other day, but the skeletal structure should be there. And sometimes it might be best if you just send me a screenshot. But there's 2 different lectures. So there's my notes, which are separate. Hang on. Give me 1 second. So I have Blackboard pulled up. So these chapter 13 or chapter 11 lectures, these are archives. So this is from last year. And so the information should be exactly the same there. Now my lecture videos go with these notes, the one package files, and there should be an associated PDF with them. So the one package is opened through the full version of OneNote. So you can get that through the school. You have access to the OneNote, or sorry, the Microsoft 360 thing, and OneNote is a part of that suite. If you can't open it and you think you have OneNote, go back to the Microsoft website and look for the full desktop version. But yes, I keep the old archives there because this is intended to be a self-run course. But I'm just offering these live lectures to help, and of course these are, at least I think, you know, they're a little bit superior just because they're interactive, but all the information's there. It doesn't matter which ones you watch. Does that clarify it? So then let's just look at, so now we have thiols here, just to kind of finish up our naming. So thiols are going to be sulfur-based groups. So these are smelly. And again, polar. So a lot of these compounds are polar. And then other compounds are aromatics. And so, like for example, this is ethylbenzene. So if we watch ethylbenzene, so 1, 2, and then draw our benzene ring or aromatic. So now let's examine more about the solubilities and kind of how we determine what things are soluble in. So if we go over, and I kind of have, I think I have more vitamins than your book has. But the whole point is we're trying to determine solubility. And then the other thing you notice with this key is, and I know I admit that this may be hard to see, the color contrast that they chose was not that great. But your vitamins can be divided into 2 classes. And this also kind of helps you with dosing. And so you have water-soluble vitamins and versus fat-soluble vitamins. So first of all, what does it mean if something's water-soluble? Is it going to be polar or non-polar? And so for water-soluble, we're looking for polar groups. Maybe a lot of OHs. And so let's examine some of these structures and why they're going to be fat versus water soluble. And so for fat soluble, these are going to be more nonpolar, maybe longer chains too. So then looking at these, so let's just go in order here. So we have vitamin A. And so vitamin A, it's got this little red border, and that's telling us that it's fat soluble. But let's see why. And so if we're looking at this structure, notice it's mainly just carbon and hydrogens. And then we also have some what's called degrees of saturation here with our double bonds. And so it only has one OH group, so that means that this is mainly nonpolar. And so that's why it's fat soluble. And of course, fat soluble, right, that's going to be stored more long term in the body, so you wouldn't want to, overdo it on your vitamin A supplements. So anything that's water soluble tends to flush out, of course, more quickly from your body, especially let's look at vitamin C for a second, because vitamin C is one of those ones where they say, you really can't overdose on this vitamin. It's water soluble. So if we look at it, right, it has a bunch of OH groups everywhere. And then we even have, right, a little epoxide ring here. So this is going to be very polar. And because it's so polar with all these OH groups, that's why it's water soluble. So let's go through and kind of look at all of them and examine. So vitamin B1 here, we have an OH group, and then we have an amine here. So that's something that you just want to be able to do. Like, can you identify our groups here, alcohols, amines? And so both of those we mentioned are polar. So that's why this is water soluble. So vitamin B12, again, I'm going to highlight, right, all these OH groups. So a lot of them, we also have nitrogens and H there. So again, water soluble. So vitamin B3 is a collection of these two compounds. So notice you have, right, a carboxylic acid and an amide there. So just identify those two groups. And of course, these are going to be very polar groups again. So polar, so that's why we get water soluble. So vitamin B5, again, examining OH, OH. Then we have, right, nitrogen, OH. So very polar again. So let's skip down. Let's look at some more fat soluble ones. I think we're getting the hang of the water soluble. So now looking at this other, so vitamin E here. So again, we only have one OH group and the rest is this long alkane chain. So again, that's going to be nonpolar. And then vitamin K. So I'm just skipping over to another fat soluble one here. So vitamin K doesn't have any OH groups on there. So again, relatively nonpolar. And so just fun facts. So newborns receive vitamin K injections to prevent bleeding. So apparently vitamin K helps with blood clotting. And newborns are vitamin K deficient. And I guess this was like a problem actually back in the day. Like, newborns could bleed out before we knew what was going on, if they had a rare condition. But it wasn't that uncommon. And then so last, let's look at vitamin D here. So again, it only has one OH group, and then the rest are just these alkane chains. So again, relatively nonpolar. And again, that's why it's fat soluble. All right, any questions on that? So now I'm just looking at your homework. And so let me know if there are questions. We pretty much covered the chapter here. So let's look at some of your homework examples. So it's asking you to examine these structures and characterize them by their formula, functional groups, water solubility, and shape around the starred atom. I'm just redrawing it. This carbon starred. So looking at this, what do we say this functional group was? So go back, can look at our chart. Ah, there it is. So we know this is an aldehyde. Okay. We also have a benzene ring here. So can we get the formula? So we have count your carbons. So 1, 2, 3, 4, 5, 6, 7. So C7. Fill in your hydrogens. Fill in the ones that aren't explicitly drawn. So 1, 2, 3, 4, 5, 6. So H6. Then O. So how would we name this? So we could look at our cheat sheet. Aldehyde. So I'm kind of curious. Yeah, see, I would name it benzene aldehyde or benzaldehyde. But I've realized that that doesn't go along with your naming. Yep, it would be benzenol. I just wanted. The only thing is, I never see it referred to as such, so that's why I'm like hesitant. So usually they're named by the aldehyde. So just in practice, I'm not familiar with people using this all ending. And so you'll kind of find that too. So if you were to Google this, and you could probably get a bunch of different answers, but either try to stick with this IUPAC name or kind of the most common. And so let's look at, so what is the geometry at this starred carbon? I'm just kind of zooming in. So again, it's attached to 1, 2, 3 things. And so if we look back from our notes from yesterday, so we had our groups here. So 3 electron groups, so it's attached to 3 things. So it's going to be sp2 hybridized with our trigonal planar geometry. And then trying to guess solubility. So of course, this is polar. But then we have our aromatic benzene ring. I'm surprised that it's not more soluble. I'm going to check its solubility. It's not like the most insoluble. I kind of disagree with this answer here. And so I'll pull up what I'm looking at to kind of. So solubility, I want to make clear, is not always obvious either. So benzaldehyde is actually a little bit polar. And so that's why I was curious. But if you look at Wikipedia, for example, it tells you its solubility. So in this case, benzaldehyde is about 7 grams in a liter of water, which isn't horrible, but I guess it's also not super soluble. And so just for comparison, because it's always good to have some frame of reference. So we know sodium chloride is super soluble in water, and so, they get 360 grams in a liter. So for that one, I'd probably be a little more lenient on it. But the main thing is you want to be able to explain too. So we have our polar group here. This has some delocalization, but this is mainly non-polar here. Let's see, let's do this one. So I'm not sure we went over how to name these. So this is a ring, and 1, 2, 3, 4, 5. So that's going to be cyclopentane to show that it's a circle. Otherwise, because cyclo and N-pentane have different formulas anyways. So no polar bonds here. So this one is definitely going to be non-polar. And just for curiosity's sake, let's see if it even has solubility. And so for this one, and this is how I would really say, yeah, this is insoluble. So insoluble, they got 156 milligrams in, I think that's supposed to be a liter. It's not quite proper, but basically pretty low. So you can kind of see the difference there. So benzaldehyde again was 7 grams. This is, essentially 0.15 grams. And then sodium chloride was 360. So you have a huge range there. So that should give you kind of a sense of what this means of, really nonpolar, not going to be soluble with water versus, kind of this slightly polar, and then versus something like sodium chloride where it's ionic with full dissociation. Nonpolar, I'll add insoluble. And then what's the geometry here? Oh, let's do the structure and formula. So first fill in all your hydrogens. So C5, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So H10. And then what's the geometry of this starred one? So carbon bonded to 1, 2, 3, 4 things. So we can always go back to our notes too. Oops, wrong notes to look at. So it's part of our 4 electron group family, right? Carbon with 4 things attached to it. And so that's going to be a tetrahedral geometry. Are there any other things you want to go over? Let me look at this one problem. So this is from our homework. And so let's see. Let's just do it. So let's do the formula. So C1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C10. Now we have to fill in all our hydrogens. So notice, right, this carbon's tetrahedral. Feeling kind of lazy, so I'll write H2 there. Hydrogen. H2, H2. Normally I draw each H. All right. So now 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. H16 and then N2S. Oh, O3. Got our oxygens there. And then what's our geometry here? Remember the Lewis dot structure of sulfur. So it's in that kind of 4 electron geometry group, except it only has 2 things attached to it. So it would look like this. So the geometry around that sulfur is bent. And then, so I think that this is biotin. So I'm just going to look up the solubility while you guess. So what do you think? Is it going to be soluble, insoluble in water? Maybe a mix even? So this one is kind of interesting, at least to me it is, looking at this. Oh, they weren't that consistent. So we have this group here. So this is our carboxylic acid group. So that can help make it soluble. We also have some NHs here. But then we also have, right, our alkane chain. And so I think your key kind of says that it's water soluble, but it would have limited solubility. So for these, I think it's good that if you give like a detailed explanation, because I'll admit, so right, this is previous material. I didn't reinvent the whole wheel here, but I would kind of slightly disagree with some of these. Or you could argue that it's maybe not that water soluble. And so if you look it up, it's 22 milligrams per 100 milliliter. So, we could scale that up to maybe 2.2. Or, excuse me, that would be 0.2 then grams at about 1,000 liters. But that doesn't sound that soluble to me, but that's what your key says. So if you kind of said that this was more nonpolar, I'll just put slightly soluble. Again, slightly soluble from the carboxylic acid, but also have our alkanes. So I think we've covered about everything. So I'll hang around on stream in case there are any other questions, but just make sure, you're staying on top of the material, getting any questions answered. And, I'm always available for office hours. I'm available after stream. We could do, a Zoom thing. Or I'm also available before lab today if you want to track me down in person. And then I'll post the notes that go along with the lecture, so you'll have updated lecture notes. So thank y'all and have a good day. So thanks again. I'll be here for about 5 minutes, then I'll shut down the stream.